Inside rainforests, every leaf is constantly breathing, releasing tiny gases that tell us how plants respond to heat, humidity, and stress. Scientists know that these signals are essential to understanding major effects of climate change. But today, they are often only measured using handheld systems, which can be slow, inconsistent, and operator dependent, or used with branch bags, which create artificial microenvironments around the leaves, leading to unreliable results. So this presents the challenge to our team. How can we reliably measure rainforest gas exchange while minimizing impact to the leaves during measurement?
Our sponsor, Biosphere 2, tasked our team, the Chlorofellas, to solve this problem. We were tasked with creating an autonomous, 3D printed, lightweight leaf chamber capable of measuring rainforest gas exchange without impacting the surrounding environment of the leaf, including gas concentration, light, temperature, and humidity.
We design our final system around these various constraints. The core of our system is a clear resin-printed chamber integrated with magnets and silicone to help prevent damaging the leaf veins throughout the system. The spherical design decreases wind drag, and the internal flow disc helps gas flow through the system without creating any dead air pockets. This chamber is lightweight, transparent, and perylene coated to remain inert and prevent the interference with the leaf's natural atmospheric gas exchange. Tubing connects the chamber with the Lycor gas analyzer, as well as the two solenoids, the air pump, and the flow regulator, all located in the electronics control box mounted to the tree trunk.
Solenoids enable our system to switch between open and closed states over 15-minute cycles. When the solenoids are open, atmospheric air is pulled through the system to flush the chamber over a 13-minute period. This prevents dead air and microenvironments from forming within the system tubing, which don't accurately reflect the leaf's actual gas exchange. When the solenoids are closed, the system creates the necessary airtight environment to take gas exchange measurements over a 2-minute period. In addition to seamlessly integrating with the Lycor gas exchanger, our cuvette design comes equipped with a set of environmental sensors all connected to our central Arduino to help contextualize gas exchange measurements. A thermistor mounted within our chamber measures leaf temperature, while additional sensors mounted on our custom-made stem junctions capture light intensity, as well as ambient temperature and humidity.
The software control interface controls our entire system, receiving gas exchange data from the Lycor, sensor data from our ESP32 microcontroller, and manages the system utilizing our custom printed circuit board. The ESP32 and Lycor connect to a Raspberry Pi, which hosts a back-end database and a front-end graphical user interface, which can be accessed remotely via the Pi's local host network. On the GUI, scientists can view environmental and sensor data, manually control the system, schedule system cycles, and export data as they please. Each leaf chamber can be constructed with only $250 and manufactured within 3 days, involving 3D printing, perylene coating, and assembly, making it easily reproduced and accessible. Our system requires only a 12-volt power source and has a minimal setup. This allows for efficient and simple deployment. Users simply clamp the chamber onto a leaf, connect the gas exchange tubing, and monitor the system through the GUI. In the future, researchers can scale up system software and hardware to support multiple leaf cuvette chambers and receive more well-rounded rainforest gas exchange data.
Our gas exchange testing focused on two key performance metrics, leak rate and flush rate. In the system's closed state, we target a repeatable leak rate of 10% or less. This ensures that the chamber is well sealed and capable of accurately measuring changes in volatile organic compounds driven by plant photosynthetic processes. In the open state, we evaluate the flush rate, targeting at least 20% per minute. This minimum rate ensures that fresh air is continuously entering and exiting the chamber, allowing the leaf to experience near ambient conditions. Testing on a live leaf confirmed system functionality and performance. In the closed state, the carbon dioxide concentration decreased as the leaf absorbed it during photosynthesis. When the system was open to atmospheric air, the system rapidly stabilized, indicated by an increase in carbon dioxide. Upon reclosing, carbon dioxide decreased again. demonstrating repeatable cycling. These carbon dioxide consumption rates, combined with the defined repeatable leak rate, enable researchers to accurately quantify plant physiological activity. To obtain accurate measurements, testing is performed using a plastic sheet rather than a live plant. This eliminates fluctuations in volatile organic compounds caused by photosynthesis and respiration, allowing us to isolate and quantify system performance by injecting known concentrations of gases. Our results show a leak rate of 0.42% and a flush rate of 32%, meeting our design requirements. At the top of the rainforest, temperatures can reach up to 140 degrees Fahrenheit, wind speeds up to 20 meters per second, rainfall up to 50 millimeters per hour, UV index greater than 11, and relative humidity up to 100%.
These models have been deployed for 2 weeks and show no signs of weathering despite these extreme conditions. We have observed no visible organic growth in the chamber, no discoloration of the leaf, no yellowing of the chamber, no debris entering the chamber, and no condensation.
Longevity testing demonstrated that our chamber can withstand the high temperature and humidity conditions in the Biosphere 2 rainforest for at least 30 days.
One of the biggest lessons learned throughout this project was the importance of early prototyping. We initially pursued a far more complex, rotating pore design, but after building and testing, we found that it could not create the airtight seal we needed. By simplifying our design and reducing moving parts, we came to the far more reliable solenoid-based design. This experience taught us that early prototyping and thoughtful design reassessment help prevent over-engineering and lead to viable designs more quickly.
Despite those challenges, we were still able to successfully develop an autonomous 3D printed leaf chamber for remote rainforest gas exchange measurements. This system offers significant advantages over current methods, including improved accuracy, repeatability, and autonomy for future rainforest research. We made project decisions that contributed to the accessibility and scalability of this project to enable researchers worldwide to contribute to collecting and researching gas exchange data. Overall, our system allows for accurate, repeatable data collection with almost no manual labor, opening the door for large-scale rainforest studies.
Leave it to